Hopefully you got a chance to download these .c files or C files from Canvas onto your Linux virtual machine. And so if you don't remember what all of these things are, I'll talk about it briefly. GCC is the C compiler, and -L pthread says that you want to use the library called pthread. So you're going to use libpthread.a or libpthread.so, shared object code. Okay, so it's not that complicated, but let's take a look at it. Okay, so I think I have downloaded it to this directory, and so I have cpu.c, common.h, mem.c, and these two other threading programs. Okay, so how do I compile this? I will do a gcc. If I try gcc and just say cpu.c, I'll get an error message, and it says I'm using this function which I'm not defining. And so here's where using the -L pthread or just plain pthread I think will work by itself. You don't need pthread is one of those special libraries that I think you can use without -L. Let's try it. So this works. So that's what the instructions in the slide tell you to do, but I'm going to do things a little bit differently, because if you look at this, you'll see that it creates an executable called a.out. I don't always want that, and so remember, you can say gcc and then specify the name -o cpu. Alright, and now if you say ls -l, you get the output CPU, which is exactly the same size as a.out, and so chances are it's the same thing. Yeah, it's pretty much the same thing. Okay, so I'll remove a.out just to avoid any confusion. Let me try another way to compile this, and I think this will work. If you just say -pthread, that should also work, and that's how most people use it, but -L pthread makes it a little bit more obvious that you're using the pthread library, POSIX threads. Okay, so now let's run this program. CPU, and then oops, sorry, you want to say CPU in the current directory, so I say /CPU, and then it tells me the right way to use this program is to say CPU and then some string, which should be a number, I think. Say /CPU2, or actually it can be any string, so let's just say p1. And then what it'll do is it'll sit in a loop and just print out p1, 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 p1. So not very interesting. Okay, but the thing is, if you have two windows, you can run CPU in both of those windows and get them to do something different in each window. And one way to sort of do that, even though I just have one display that I can use, is to sequence these programs. So I want to say CPU P1, and that'll run in the background while I start up other program. I'm just going to make another copy of the same, and I have the same program run in another process. And this time I'm going to say P2, and then you can see they're both running P1, P2, P1, P2. Okay. Hopefully, oops, they're still running. Oh yeah, now I have to kill this. So I'm going to create a new tab. I'm going to say PS, PSA. Now I got to find, oh yeah, here it is. Here's one of them. So I'm going to kill this. Kill -9, 311, 87. And let's take a look over here, see what happened. Now one of them dropped out, it's just the other one that's still running. And so where is it? There should be another CPU running, but I don't see it. Let's try. Oh, I think I killed it already. Yep, I did. Okay, so I actually did a control C before, and one of them got killed, and then when I did kill, it really got the one that was left behind got killed. So these are things that you will run into. Chances are you've probably seen all of this from CSIS 248. If not, you want to try to get used to all of these things as soon as possible. Okay, so what we did was, so once again, let's try this once again. This time I will put an ampersand over here. Okay, so how is this different? This is basically saying run one copy of the program CPU with the input P1 in the background, and then start another copy of the same program and give it the string P2 and run both of these in the background. You get the same output, but this time around, notice I got two processes, 31215 and 31216. And if I hit Control C, I actually don't do anything. They're both running. Whereas if you start this video again, you'll see that when I hit a Control C before, I was able to kill one of them. So what do you do when you have this situation? If it scrolls past too quickly, you might not be able to see these numbers, but all I have to do is use these two process IDs and kill these two processes. So 31215. So kill -9. I know it's kind of hard to read. So I killed one of them, I think. Yep. I said enter and it got the killed message, but the other one is still there. And so gotta find that number. Sometimes you might have to open up another tab to find out these numbers. So 31216. So kill -9 31216. I know it's hard to read, but yeah, I think you'll get used to it. So these are the kinds of things you want to be able to do soon. So let's take a look at what this program is doing. Very simple. All it says is I'm going to have a main program and checks if you have two things in the command line. If not, if it's not equal to 2, if you just have one, prints out this usage message. And then it says, well, what is the string that you pass in as an argument? And what I'm going to do is I'm going to just sit in a loop and keep printing that whatever argument that you passed in, so P1 or P2. And so it just sits in a loop, and the spin, it doesn't really do anything, really just waits. You can look it up. I'm just going to quit out of this. So just remember, this program really doesn't do anything. It sits in a loop and prints out a message, okay? But it's important. You're sitting in a loop and you're not quitting, you're just doing one thing. So if you look in common common.h, you will see the function spin. It just takes an argument that is how long it's been doing something. So this actually doesn't really do anything. It just sort of spins its wheels, as we say in operating systems. Okay, so once again, if you run these two programs, right, they're just spinning their wheels, printing out whatever you asked them, whatever you gave them as input, P1, P2. One does P1, one does P2. They're both running at the same time. And the only way to distinguish between them is that we gave them different strings. Okay, so remember, you cannot control C it this time around. Doesn't work. I'm going to show you how you can create a new tab, and you can say PSA here. Now we see both of those, and you say kill -9 You can't say kill all instances of CPU. There are ways to do that, but this is better. You know the exact process ID, and you kill them, and you look back here, you just hit enter, and it'll print out this message saying both of these were killed. Okay, so make sure you can do this. Make sure you can have multiple copies, not just two, maybe 3 or 4 or 5, and have fun. Okay. So let's take a look at this program. It's very simple. It looks like each program has its own CPU to run on, and that's really what what the operating system does. So operating systems virtualize the CPU by using what's called the process abstraction. So we just saw that we created two processes. A process is just a program that's running. When we think about programs, we think of code sitting on a disk, but that's not really all. The main thing as far as what we're concerned is in this course is what happens when that program is running. Okay, and how do we prevent those two? In this case, when we just looked at two processes that were different, but they didn't like trample over each other. They kept everything separate. Well, the output definitely were trampling over each other, but you could run each process in a separate window and you would see just the output of one. Okay. So a process is an execution stream within a context of an execution state. So what is an execution stream? It's a stream of instructions executing within some thread of control. Execution state is everything that affects this instruction stream. So the CPU registers, the heap, the stack, open files, and other data. I'm guessing that you've seen all of these things defined in either CSIS 248 or 355, but this course will make you put all of these ideas together. Okay, so you have to think about all of these things in a much more like a cohesive way. So what is the difference between a process and a program? So we saw that CPU.c that was some static code with some static data. That's just one program, but we create multiple processes. You can create more than two. You can create as many as you want. You can write a shell script to create hundreds of processes from the one program. So what is a process? It is code that is currently being executed, changing data, and changing data only for that one process. Okay, so when we saw how we can distinguish between those two processes by giving it different strings, we can sort of track them, see which one's running and so on. We can kill one of them, the other one is still going, it's not affected. You can kill both of them, and then yeah, there's no more processes that are instances of this one program. So we can run multiple instances or processes of the same program. We can create as many as you want, as we're only limited by the resources, total number of resources that we use. So once again, a program is code and some static data that's sitting on a disk. And this is sort of the operating system sort of breathes life into this program and has it running. It loads it into memory and uses the CPU to actually run this program. Okay, so when you create a process, what you're doing is put this into memory, start running instructions one after another. So we have a code segment of memory, we have some static data maybe, like we don't have any in this one simple program, but often you have strings and things like that that you store in your program. Those are considered static data. We have the heap and the stack as well. Okay, so this is all discussed in chapter 4 on processes. Definitely read section 4.3, that's pages 4 to 5, on process creation for how processes are created, but here's a simple idea. You take your static code and all of that and your file and load it up into memory and start executing instructions. That's how programs run. Okay, so hopefully you get a chance to look at how a basic program works and get used to the idea of processes versus programs. They're two different things. You can have multiple copies, and so remember that if you have a machine where two users are using the same machine, one user types in a utility command like ls or cp. That doesn't change what the other user sees, even if that person is running the exact same program, right? They don't trample on each other. Okay, so we'll take a look at how the operating system makes it like that. But next, let's take a look at virtualizing memory. So let's take a look at mem.c. You compile it using GCC, and then we'll see certain things that we'll have to maybe do a little bit more complicated thing to run mem.c the way we want it to run. Okay, so here we are. We have the CPU.c. We say GCC. Let's just try GCC mem.c. We got the same error message, which means we have to say GCC minus o mem, and then we need this minus l pthread, and it's because we didn't have the minus l pthread that we got this error message saying what are these pthread things. Okay, this time of course it works, and then we want to run this program mem /mem, oops, and then it gives us a usage message saying type in mem and then a value. So I'm going to say /mem, and then I'll start with the value 6. Okay, so it prints out a bunch of things. I'm going to Control-C it and stop it. Okay, so let's take a look at this mem program, but you can sort of see that whatever value we passed in here, it increments it and then prints it, increments, and prints. That's all it does. And so this value 6 is going to some variable p, which is then incremented in a loop. And you can see that the address, memory address of this variable p is a hexadecimal number. So review your hexadecimal if it's been a while. And it turns out that you're printing not only the address of p, but also the address stored in p. So these are two different things. Okay, so let's see how mem.c is set up. Okay, so as before, I know it's a lot of code, so take your time and look at it slowly. You can pause this video and go through it really slowly, but as before, we have an if statement to check if when the program was started, it did have an argument. And so this variable p is actually a pointer to int. Okay, so the p variable, you allocate memory for it, but what's in it is actually a pointer. And we say that the p variable is going to have the value, which is the address of value. If this is a little confusing, definitely you want to stop and maybe think about it and go over your notes from CSIS 248, because those are the kinds of things that you will run into, you probably ran into in CSIS 248. Okay, so ultimately what happens is, so you have a pointer p which points to value, which is a global variable, and that's considered static data actually. Okay, and we put whatever argument that the user types in, like I put in /mem and then I believe 6, And so now you want to be sure you know or understand what this statement is doing. It takes that argv thing, which is 6, converts it from ASCII to integer, stores it into the memory location pointed to by P. So that's what this one statement does. And after that, sits in a loop and uses the spin again, doesn't just waste time, and says increment the the value of the thing pointed to by P by 1 and store it in the location pointed to by P. That's a mouthful, but basically what it's saying is whatever P points to, increment it. Okay, so make sure you understand this is a nice simple program, but think about it and see how the output works. That's the kind of thing you'll be doing a lot of this semester. I'll give you programs, you have to think about how it works, figure it out. I know it's a lot of work, but that's you'll be doing a lot of that. That's a really good skill to develop. Okay, so let's say we run this again and we give it different values. So mem.c6, and then I know what will happen. Let's just keep going. So let's say I do a mem.c, sorry, /mem and 7. Okay, and so now take a look at the differences between these two runs. So it looks like the address of P, so P is located in memory, it's in the stack, and once you get used to this, you'll probably recognize that this is somewhere in the stack. And remember that value itself, that was stored in static memory, and it has a completely different type of address. Each time you run it, you get some things that are similar, like the 7 is the same, and the 7FFF is the same, and that's a good indication that you're looking at something in the stack. This 5 something tells you that you're looking in what is called static text or global data. So that's a global variable value. So remember, P is a pointer to this location, which is where we actually store the 8, the 9, and 10, and so on. Okay, so there's a bunch of things going on. Every time you run this program, this will be different. Okay, that is actually not because of the number that I'm typing in after /mem. You got something different here. See if you can detect a pattern. There's actually no pattern. Trick question. If I go back to 6, now I might say I should see something ending in a 3BDO, because that's what we got before. Well, try it. And oops, scroll past. So we had before, when you said /mem6, got something ending in a 3BDO. This time it's something completely different. When you do the same thing many times, you get something different. There is no pattern. It's actually random, sort of random, because that is a security mechanism, security feature that programs in Linux and Windows too have. It's called address space layout randomization. And what it does is change the location of the stack every time you run the program, so that people who write malware don't know where the stack starts and therefore cannot use buffer overflow attacks. Yeah, so we're going to get into a bunch of different things, but what we want to do right now is just turn it off. And you can do that in GDB. So GDB is the debugger. So I'll say GDB mem, get all this stuff. And then now I can run this program. So you can say run, but that's not enough. I should give it a number. But if you don't give it a number, it'll tell you you have to give it a number. Say the usage is to say mem and value, that error message. Okay, so I'm going to say run and then 2. And there it goes, it's running. So I control C this. Okay. I know it's kind of hard to read, so you might want to pause the video every once in a while, see what it's, or just run this program on your Linux virtual machine. So now I say run 2 again. So oops, run 2, and it says program was started. Should we start from the beginning? Say yeah. Okay, let's take a quick look. Here, the address of P. Oh, all right. I think I did disable. Let me check. Show set. I think I ran this before. Go back and look at the slide. Show disable randomization. All right. Show. I think I disabled it before. Do I need a? I think I probably need a hyphen. Just did a backspace. Oops. Disable. Disabling of the debuggies virtual address space is on. Okay, so I did disable it earlier, and that's why if you run it twice, even with different things, so Control C it and run it with a 3 or 56 and start it from the beginning. Control C that. Okay, so now that I've disabled randomization, I can see that these addresses in the stack always start with the same value. So you have to do you have to disable address space layout randomization, which is a security feature, and now that you've done that, then you'll get the exact same addresses every single time. So that's important. Okay, so there is a security feature called address space layout randomization. Once you disable it, you'll see that whenever you use this program, you're using the same memory locations. And earlier it was different, not because the program uses different memory locations on purpose, but because of the security feature. So I'm going to restart it up, set disable randomization off. That is, I want to enable randomization. Okay, let's show it to double check. Okay, so we turned off the disabling randomization, which means randomization is on. That's what we want. All right, I'm gonna quit. Okay, so let's take a look at this code. So based on what you learned in CSIS 248, that is operating system programming, if we run multiple instances of this program mem, are we actually accessing the same physical RAM location? It sure looks like it. Once you disable randomization, we get the same memory addresses, and looks like we are using the same physical RAM location. But it turns out no, we aren't. So are we using the same physical RAM location? The operating system makes it look like we are using the same physical RAM location, but this is actually not the real physical RAM location. We are using a process address space, or which is also called a virtual address space or virtual memory. Okay, so the OS takes these memory locations that we think we are using and in the background maps them or converts them to the actual physical RAM locations. So when we think that we see the physical hex addresses, we're actually not seeing the DRAM locations. There is a layer of mapping, a virtual memory component of the operating system that converts these values to a different value. So you can have multiple, that's what allows you to have multiple copies of this program mem. You can try this, definitely recommend you trying this. Take two shells and run mem in both of them. They won't trample over each other. They won't write over each other's programs. They'll be changing data, they'll be using pointers and stuff like that. Even if you disable randomization and it looks like you're using the same memory location, they're really not, because there's a layer of operating system functionality that we don't see in the outputs shown here. So behind the scenes, once again, the operating system maps the addresses that we think we see, like those stack and global data, global memory locations, to actual physical RAM locations. Okay, so the operating system makes sure that each process gets its own virtual address space. So we'll go into a lot of detail about how all of that works, but it'll take a little bit of time to get there. Before we get there, let's talk a little bit about direct versus controlled program execution. So in direct execution, we allow a user process to run directly on the hardware. So this is what DOS used. I know DOS has not been around for a long time. Maybe some of you used it for certain games, but that was one reason for using DOS, was that DOS allowed you to run directly on the hardware, so you could use all of the graphical features that directly, and so that was efficient. It could be efficient use of hardware. However, there are a lot of problems with using direct access to hardware. It can break security. So you only have one in DOS. In the original DOS program, there was only one user. You can change everything. You have access to everything. You can use the CPU forever. You can write an infinite loop and no other program will ever get to run, because you have complete control over the CPU. As far as efficiency, you may end up busy waiting for, if you have a slow disk or something, you end up doing a lot of waiting. It's generally not a good thing to do, and we'll talk about all of this efficiency and things like that as far as I/O much later on this semester. So while direct program execution may come in handy for some things when you need complete access to the hardware, it is not a good thing for general purpose computers. So, and the solution was to use an operating system, and you maintain some control over what these processes can do, which means you can't do anything that you want anymore in programs. You have to play by the rules. Okay, and so that's called controlled program execution. The OS controls. So the main way we do that is to set up two levels: the user mode and the kernel mode. So user mode is restricted. You can only access some parts of the memory, unlike DOS, where you can access anything you want in your program. And kernel mode, where you can access everything, but this is only for trusted, basically operating system programs that can run in kernel mode. Okay, so if you ran a program like we were running MEM and CPU, those were processes running in user mode. They can only do some things, whatever the operating system allows you to do. The operating system kernel itself runs in kernel mode and has access to pretty much everything. Okay, so how do we enforce security? So how do we prevent processes from trampling over each other's data or memory, things like that? Well, processes have to use certain what are called system calls to access valuable resources, and these system calls are checked by the kernel. Okay, so every process running on a system is in one state at any given time. Either it's running and then it gets descheduled by the operating system so that some other program can be running, in which case now this is going to be switched to ready, unless of course you have multiple cores, in which case you can have multiple programs actually running at the same time. But let's just say that for now that we only have one core. And so program is running, some other program needs to run, you deschedule it, you go into the ready but not running state and let some other program run, and then when that program gets a chance and now our program has to run again, the OS says, okay, this thing is ready, I want to run this, I'm going to schedule it to run, and then goes back and forth until you want to do some IO, that is read from a disk. And we'll talk about how slow things are on disk, because as soon as it says I want to read 1 byte from disk, the operating system says, okay, this will take way too long, I'm going to start the disk reading, but by the time it's done I would have probably executed 100,000, maybe a million other processes. So operating system, what it says is, okay, I'm going to block this process, this process wants to read a single byte from disk. I'm going to block it, let a whole bunch of other processes run, and in the meantime I start the process of reading that 1 byte. It takes a long time, and then when the disk says, okay, here it is, then I will say, okay, now it's ready to go, it's no longer waiting for something from disk, and then it gets scheduled and runs again. Okay, so this figure is super important. Everything is important, but this is especially important, and make sure you understand how processes are scheduled. Okay, so now let's come back to this idea of a process address space. We'll flesh this out little by little. So let's say you have a program A, it's running, and so it's now a process, and it wants to read something from disk. So it will call the sysread function to access the disk. So remember, this is a user process, it's in user space, and this is all it's allowed to see. There may be other processes running, but you can't see it, and you can't take a look at the kernel. If you try to access, if you even try to read something in the kernel, well, that'll set off a trap, and it'll say, okay, this is trying to violate access control rules, and it gives you a segmentation violation error and crashes. Okay, so you can only access things in here, its own memory. Other processes and the kernel are hidden. There's no way to call this sysread function directly. Instead, what you do is you call the read library function. Okay, so you call read, which runs in this user memory, user space, more accurate way to say that. And then read takes care of calling sysread, system read. Okay, so it's a very important distinction. So process A can only call read, it cannot call things in the kernel. If you try to do anything in the kernel directly from here, your program crashes. So sysread will do this. Actually, this is the actual instructions that read will do. So it says, okay, I'm going to access this system call table index. Okay, and then I'm going to say, I want to call the sysread function, which is in the kernel, and here's a trap that says, okay, now operating system, take over and execute the sysread function, which is indicated in this message. So you store something in a register and then say, okay, I give up control over this program. Operating system, go ahead and interpret the system call and execute the code over here. Then what happens is, as soon as you execute that interrupt, the CPU switches to kernel mode, and now executing as kernel, everything is green. That means we can do everything. The kernel can do all kinds of stuff, and then get that 1 byte from memory and put it in some space where A can access it, and then says, okay, A, you're going to run again. Okay, so keep that picture in mind, because that's really important. That's how you make system calls. The kernel can access user memory. So remember, you cannot access kernel memory, but the kernel, once it does that read a single byte, it can store that into some address location inside your program, and then when it's done, So I mean, when it reads that stuff from disk, it's stored up here, and then when it's done, it gives you back control. Okay, so what are user processes not allowed to do? User processes are not allowed to access memory beyond your own process address space. It cannot really access disk even though you're reading stuff from disk. What you have to do is go through the operating system to read even a single byte from disk. You might say, what's the harm in reading a single byte? Well, a lot of things can go wrong. And so when you try to read something from a file, a single byte, you actually have to do this big long procedure where you say, okay, make the system call, kernel, take over. The kernel kicks in, reads that byte, puts it in here for you, and then puts you back into this mode. You're running again, and to you it looks like you executed this read function and read something from disk, but actually what happened was you gave control over control of the CPU back to the kernel, and then kernel gives it back to you, and then you're off and running. So there are a whole bunch of privileged instructions. So I'm using the example of x86, which is 32-bit CPUs. 32-bit CPUs have 4 rings: ring 0, ring 1, ring 2, and ring 3, out of which only 2 are used: ring 0 for kernel mode and ring 3 for user mode. 1 and 2, rings 1 and 2 are just not used by any operating system, except from some specialized ones. Just doesn't work. Although the hardware people just thought that maybe we'd have multiple rings and you could use it. It was just too complicated. We only used 2. There's negative rings, and we'll talk about that later. Not yet. So for now, just pretend you have, even if you have 4 rings, you only use 2: ring 0 and ring 3. When you do an interrupt and you switch to kernel mode, so now you're running in ring 3, you can only execute certain instructions at that point. There are some special instructions that only the kernel can execute, and that only happens after you get to this point, and now it's the kernel running, and there's a chunk of memory, or it's like 2 bits in memory, that says in the CPU, okay, we are now running in kernel mode, that is supervisor mode, ring 0, and which says that now the kernel can execute a whole bunch of other instructions that are not visible to regular users. Okay, that's really important. That's how the operating system protects these different programs, by allowing only the kernel to execute in ring 0. And so one of the things people try to do is root a system. There, what you want to do is get access to privileged instructions, privileged mode, or ring 0. You become root, and you get access to these privileged instructions and things, and then you can do anything you want. So it's related to rooting a system. So what are some privileged x86 instructions? There's all these global descriptor tables and local descriptor tables, things like that. Task register. You can do all these different instructions in privileged mode that you cannot do in user mode. If you're in ring 3, if you try to execute this, you would just get an error message and your program would crash. Okay, so these are just examples of programs that you can use. You can, for example, halt the processor, something that you can only do in ring 0. You cannot write a program in user mode to halt the processor, because then you can stop everything. Okay, so how does an operating system control access to the CPU? So to allow an operating system switch between 2 processes, you have to be able to stop one process, save its execution state, and switch to another process. Okay, so let's say you run a process A for some amount of time, that is its time slice. You stop A and then save all the context, which is the registers. I'm going to just pretend that that's the main thing, is that the context of a process, it's register values, and that's a big part of it. But there's also all kinds of memory locations and things you have to track also. And then you load, once you've saved the context of A, that is all the registers of the CPU that relate to A's state, you load from memory the register values for process B, and you start process B running, and then you do the same thing. You let it run for a time slice, and then you stop B, and maybe you save the contents of save the context of B, and then you load the context of some other program C, or you load A back. And so that's what happens when you scroll back up and you do this. A is running, and then you need to give some other process a chance to run, so you deschedule it, and so you're saving the context of A, all the registers and things, to memory. There's some other process that's in the ready state and waiting to run. You take that other process, put that from the ready state to the running state, and then load the context of that other process into the CPU registers, and then say, okay, run for a time slice. Okay, so those things are really important. If any of this is not clear, definitely you should ask questions in the discussions or in class. Okay, so this is called context switching. Very important term. You're switching the context from A to B. Think of it as, this is called multitasking, and multitasking is a term that was used in computers only, pretty much. And then it became used in popular parlance or popular speech. We talk about people multitasking. Well, that actually came from computers. And the idea is that these days people think that they can watch TV and do homework, or watch a movie streaming video and do homework. Well, you can't, because you actually have to do the switching. And the deeper the problem is, the more complicated a problem is. Let's say you're running, you're not running, you're thinking about something. The time it takes you to do this context switch and switch from, let's say, debugging a program to watching a video is so huge that it's just not efficient. It's not like multitasking in a CPU. In a CPU, this context switch always takes a teeny tiny amount of time, and it works every single time. If you try to debug some code while you're watching a movie, going back and forth is so hard that you just don't want to do it. You stop. You basically do something else, right? You just concentrate on the movie, and you're done with it. Concentrate on debugging. You cannot do both very effectively. You can probably do things like that, but it'll be so slow, it'll be very inefficient. Okay. All right. So how do you control access to the CPU? So in the hardware, what you get is a timer interrupt. There's a timer that's always running, that's only accessed by kernel code. And so you do a context switch, you save all the registers of process A to the kernel stack, switch to kernel mode, and you want to then jump to the trap handler, which will execute the scheduler, which says, okay, I want to find out the next process that is waiting to run but hasn't run for a while yet, and I'll run that. Okay, so that's all operating system code that does all of this. And then after some amount of time, so this is time, and let's say process A got to run for its time slice. The timer goes off saying, okay, time slice should be over now. You do the operating system kicks in and does the context switch, moves the state around and says, okay, I know that it does a bunch of figuring and realizes B is waiting and should be able to run. And then it says, okay, do the context switch for B. I'm going to restore the registers of B to the CPU from the kernel stack. And then so you move to user mode, and then you do this jump to B's instruction pointer. That is basically saying this is a register. IP instruction pointer, or program counter is probably another term for IP. That's where the next instruction that has to be executed is stored in memory, and that basically says, okay, start execution. of where we left off in B. Okay, so I'm hoping all these things, all these terms are coming back to you from CSIS 355. And we'll revisit some of those topics. They're really important. So let's take a step back and take a look at CPU virtualization. The goal of CPU virtualization as far as the operating system is concerned is to run multiple processes, like n processes, on m CPUs, where the number of CPUs m is smaller than the number of processes in general. Okay, so that's actually pretty much always happening. In any Windows system, you will probably have hundreds, maybe thousands of processes running, even if you have one core. And these days, of course, you cannot get CPUs with just one core. You get 2 or 4 or 8 or 16. So, well, that number is small. The number of cores is actually not that big. The number of processes is almost always much larger than the number of cores. If you have DOS, of course, you only have one thing running. You can make do with a single processor. But with multitasking or multiprocessing, which is what things like Linux and Windows and Mac OS X use, the number of processes that are supposedly running at any given time is much greater than the number of cores. And how does that work? Well, the operating system gives you this abstraction called a process. It says, okay, each program will have access to these resources, and it does all the dirty work in trying to make it look like the program has complete access to those resources, when actually you are sharing the CPU and memory and all of that with all of the other processes. So OS takes care of giving each process the illusion that it has access to the entire machine. So we need a lot of support in the kernel and the CPU to do this CPU virtualization, to give each process the illusion that it has access to the entire machine. Okay, so I'm going to end with just having you take a look at these two programs. We looked at cpu.c and mem.c. Take a look at them, make sure you understand them, but then also take a look at threadv0.c and threadv1.c. Okay, take a look and see if you can figure out how all of these four programs work. Okay.